Hey guys, in this video we're going to be introducing inverse variation relationships with a really visual example. In this case, I have here this purple rectangle with a base of 2 units and a height of 12 units. And this information, you found it here at the left. This means that this rectangle has a total area of 24 centimeters squared. Now, imagine a problem where they tell us that the area of a rectangle has to be fixed, but you can't change the lengths of the sides. So let's say, to continue with this example, we want to build another rectangle that has an area of 24 centimeters squared, but has a different length and a different height. For example, two numbers that we can think of is a base of 3 units and a height of 8 units. So I can drag this point, point C, to the left and bring it down to 3 units. Immediately you notice that the point B has changed a little bit until 8. On the left you see some approximations. We can improve them. Right, there you go. Now, you can keep on trying to think of other rectangles. For example, a rectangle that has a base of 4, which would be having a height of 6 in order to maintain the same area of 24 centimeters squared. Or you can also keep on going until 6, which would then have a height of 4, and you will have infinitely many other rectangles, because those examples I have been showing you are examples that only consider whole numbers. But you can also, whenever the base is a decimal number, there will be another number that will help me get to an area of 24 centimeters squared. For example, look over here. If I have a base of 2.68 units, the height would be about 8.97 in order to achieve an area of 24 centimeters squared. Now, if you notice how I drag this point seems to follow a curve that is decreasing the more I move to the right and increasing the more I move to the left. So this line that this point is following is the line, or is the curve, of an inverse variation relationship. And you see here on the left its equation, that is 24 divided by x. That means I chose the base of the rectangle that I wanted. To obtain the height that should agree with that, in order to achieve an area of 24, I would need to divide 24 by x. Okay, so that is the curve that appears. We will be understanding a little bit more with a second example. So imagine now that we changed the restriction. Now we want squares that have an area of 36 centimeters squared. Here you have, let's say, our first example that can be base 3 versus a height of 12. Now, once again, I can start thinking of different things. For example, another rectangle, in this case a square, that I can think of is, for example, the one of 6 by 6. This one also works for all of us to achieve an area of 36 centimeters squared. Okay, once again, approximations are not easy, but here we saw them. This point, once again, is following somehow a curve, that if the base is longer, the height will be shorter, and if the base is shorter, the height will be longer, in order to achieve the same height, the same area that we want to achieve, that is 36 centimeters squared. Now, once again, I can show you the curve that is following this point. If I choose a definite base, for example, in this case 2.56, in order to obtain the height, you divide 36 divided by that base. Why? Because the base times the height would give me the area that I want. Now, let's hide the squares and show the two curves. So here you see these two curves that go down. Inverse variation relationships look always really similar to these two curves. You can identify them in the first quadrant of the rectangular coordinate grid, because as the x, or independent variable, is increasing, the y, or the dependent variable, is decreasing. Now, if I move left, when I decrease the independent variable, the dependent variable would increase. Okay, and you can see how this happens even if numbers are larger. Okay, I invite you to watch the next video on inverse variation relationships in order to see other properties that inverse variation relationships follow, such as its asymptotes, symmetry lines, and sister functions. See you later then.